So, now another method to see how a wavefront is divided into two portions and made to interfere, that is division of wavefront, is Billet's split lens interferometer. This is very popular. One question has been already asked in IIT also. So, let us see what is this Billet's split lens interferometry. In this method, a converging lens is used. This is a converging lens. This lens is cut into two portions, split it into two portions, and then we place this lens, we displace this lens some distance delta apart. So, when this lens is split and displaced, then this lens, the optic axis of this lens is there, this is lens L1 and this lens L2, and the optics axis is this. So, you can say this is A1 B1, the optic axis of lens L1, and this is A2 B2, the optical axis of lens A2 L2. So, this is Billet's split lens. Now, a source is kept in front of this split lens, and the image due to this upper lens and lower lens is used to produce two slits S1 and S2, and again the waves from S1 and S2 are made to interfere. Let us see how it is done. Now, you see, this is my two split lenses L1 and L2, and a source S is placed at some distance greater than here 2f or anything. We can change this distance, but let us, in my diagram here, this source S, because of this lens, forms an image here, and because of this L2 part forms an image here. These are real images. So, you can see here the wavefronts from here, you see this wavefront converges here at S1 and then here again diverges. So, from the upper half of the lens A1 B1 is the region illuminated. Similarly, the same wavefront here, you see this same wavefront here is an obstacle so that the rays do not pass through here, that is not shown in the diagram. So, the same wavefront gets refracted from the lower half and they converge at S2 forming a real image S2, which after converging goes to this, and thus A2 B2 is the region illuminated by the wavefront refracted from the lower half H2. The interference pattern you see here, this is the region where we get the two waves interfering, and this is the interference pattern. So, in order to calculate fringe width here, we require the positions of S1 and S2. What things I require? I must be given the object distance, the focal length of the lens, and this distance is suppose L or B, anything we can assume, and we have to calculate S1 S2 by geometrical optics, and this distance also by geometrical optics. So this is how the interference is formed. This is the region where interference fringe will be there. So we will now calculate that what is the fringe width and how many fringes will be formed at these locations. So first of all, we have to calculate where is the image formed using the lens formula. So you see, lens formula is 1 by V minus 1 by U is equal to 1 by F. 1 by V minus 1 by is equal to 1 by F. So we will calculate V. So U is here A, this side minus A, so it becomes plus A, and 1 by F. Focal length is positive for converging lens, so 1 by V becomes 1 by A F minus 1 by A, that is again F into A by A minus F, that is V is F A by A minus F. This is this distance. Now let us calculate what is S1, S2, this distance. This will be your D. So in order to calculate distance, this distance D, this is D and this is delta, we use similar triangles. We will draw next other diagram, so that where I will not draw wavefronts, so our diagram will be neat, so that we can study it in a better way. So now I have again drawn the diagram. This time I have not drawn the wavefronts, so that my diagram is neat to study the distances involved. Now first calculate, let us calculate S1, S2, the slit width, the distance between the slit D. So we see these two triangles, this triangle and this triangle I have drawn here, they are similar. So this distance is A, the object distance, this distance is V, which we earlier calculated as F A by A minus F. And so let us calculate what is S1, S2. So S1, S2, we can write S1, S2, this by delta, this by this is equal to total distance A plus F A by A minus F. Here A distance should be greater than F in my diagram, since this is a real image. So a converging lens can form a real image only when this distance is greater than F. Otherwise this image will be virtual, and with virtual image also we can get, but the diagram will be somewhat different. So by this distance A, this similarity say, so S1, S2 by delta is equal to total distance this, that is A plus this divided by A. So this on calculation gives A square minus AF plus AF by A minus F divided by A. So S1, S2 by delta, delta is the displacement of lenses, that this cancel out. So it will be A square by A minus F, A square by A minus F into A, that will be cancelled out. Implies S1, S2 will be equal to delta times A minus F, delta times A into A minus F. This is S1, S2. So I think we can represent, okay, let it be delta. So S1, S2 we got the distance between slit widths. Now we further require the distance from the slits to the screen, that is denoted as capital D. So, capital D will be here L minus that V, L minus V, L minus V. V is already F A by A minus F, that is AL minus LF minus AF by A minus F. So, we got D. So, once I got S1, S2 and D, then fringe weight simply is written as fringe weight beta is equal to lambda D by D. This is the formula. So, here lambda D by D, D means this distance and this D is here S1, S2 is equal to delta A by A minus F. So, I am writing here it here. So, if you have copied, I will write it. So, fringe weight beta is equal to lambda D, that is AL minus LF minus AF by A minus F, that is lambda D by D, that small d is S1, S2, that is delta A into A minus F. This A minus F cancels out. This becomes lambda AL minus ALF minus AF by delta into A. This is fringe width. So, this is the fringe width formed here. Now, fringe width beta is calculated, interference is within this region, and now the total number of fringes. In order to calculate total number of fringes, we further require this distance, which we can calculate from again similarity of triangles. So, you see how, so this triangle is similar to again this triangle. So, you see this triangle now again, let us draw this triangle, this is delta and this is A, and we require to calculate, here is the interference pattern formed here, this region interference, here to here interference is there. So, this is, we call this A1, this is A2, this line will be somewhat like this, A2, this is B A1, and this A1 B2. So, whatever you call it, it is A1 B2. So, whatever its name is, A1 B2. So, we calculate this. Now, already we know that this total distance is A plus L. So, by similar triangles A1 B2, this distance by delta will be equal to total distance A plus L by A, implies A1 B2 is equal to delta A plus L by A. This is A1 B2. So, now we know this region where interference pattern is formed, I know beta. So, total number of fringes will be this upon this. So, total number of fringes. So, total number of fringes N is equal to A1 B2 by beta. So, that N will be equal to A1 B2, that is delta something A plus L by A by beta, that is lambda AL minus LF minus AF by delta A. If A cancels, so we can, and here delta, so this becomes delta square A plus L by lambda AL minus LF minus AF. This is the total number of fringes. I hope there is no minor calculation mistakes. So, this is the total number of fringes formed, and so important point here we have to understand that a lens in Billet's split lens, a lens is split into two portions. and displaced, so their principal axis shifts, and then the source is placed in front of them, and the source forms a two real images which acts as S1 and S2 as virtual source, which were allowed to form an interference pattern here. So we got beta, this is the beta, we got where the fringes are formed and how many fringes will be formed. This is how we do it. Next we will see, let us see that if we will see two things, the lens is displaced not normal to the optical axis but along the optical axis, one modified case, and another case we can put S closer between focus and the pole so that the virtual images can be formed, and some other modifications can be done.